The black box is not black. It is bright orange, required by regulation to be that color, so it can be found in wreckage. It is not a box, it is a rounded, cylindrical assembly, shaped the way it is because corners concentrate impact stress and a cylindrical profile distributes it. And it is not one device. Every commercial aircraft carries two of them, a flight data recorder and a cockpit voice recorder, which serve different purposes, record different information, and are physically separated in the aircraft so that a single catastrophic structural failure cannot destroy both. Those are the three things most passengers think they know about the black box and have wrong. The fourth is the most important. The bright orange housing most people picture when they hear the words is not the part that survives anything. The part that survives is a separate unit inside it, the crash-survivable memory unit. A cylinder roughly the size of a tennis ball canister, built from three concentric layers of material, each one defending against a different kind of destruction. This is how it is built, what it is built to survive, and the two times it was tested by real accidents in ways that exposed both the full capability and the real limit of the engineering. The aircraft's physical state throughout the flight. Altitude, airspeed, heading, vertical acceleration, control surface positions, engine thrust, flap settings, landing gear status, and dozens of additional parameters depending on the aircraft type. Modern commercial airliners record between 88 and more than 1,000 individual data channels simultaneously, sampled multiple times per second, stored on a continuous 25-hour loop. The newest data overwrites the oldest, so the recorder always contains the most recent 25 hours of the flight. When the aircraft is destroyed, the recording stops wherever it stopped. Investigators get the final 25 hours, or the entire flight if it was shorter than that. The cockpit voice recorder captures audio, 4 channels simultaneously. The captain's microphone, the first officer's microphone, a third crew member microphone if present, and an area microphone mounted in the cockpit ceiling that captures all ambient sounds, engine noise, alarms, switches being thrown, conversations between crew members, radio communications, and anything else audible in the flight deck. The CVR runs on a 2-hour continuous loop. The oldest audio is constantly overwritten. If a crash occurs, investigators receive the final 2 hours of cockpit audio leading up to it. The two recorders are physically separated in the aircraft, typically installed in different locations in the tail section, specifically so that a single impact or structural failure cannot destroy both simultaneously. If one is damaged, the other may still be intact. The data on one informs the investigation even in the absence of the other. They are redundant not in function, but in location. Both recorders are installed in the tail section of the aircraft, typically in the aft fuselage, as far back from the cockpit as practical, for a specific structural reason. In most crash sequences, the nose of the aircraft contacts the ground or obstacle first. The impact force that destroys the forward fuselage propagates rearward through the structure as the aircraft decelerates. The tail section, being the last part of the airframe to reach the impact point, experiences the deceleration later and typically at a lower peak force than the nose. This is not a guarantee of tail section survival. Crashes vary enormously in geometry and severity, but it is a probabilistic advantage and one that has been borne out in accident investigations. The tail section, and the recorders mounted within it, survives more often and more intact than the forward fuselage. The regulators who wrote the installation requirements understood this and codified it. The recorders do not need to be in the safest possible location. They need to be in a location that is safer than average, combined with construction that can tolerate the difference. In 1934, a small passenger aircraft called Miss Hobart disappeared over Bass Strait in Australia. Among those killed was its passenger, Reverend Hubert Warren. His son David was 9 years old. 19 years later, David Warren was a research scientist at the Aeronautical Research Laboratories in Melbourne, working on the investigation into a series of fatal crashes involving the de Havilland Comet, the world's first commercial jet airliner. The comet crashes were mysterious. Without any record of what had been happening in the cockpit before each one, investigators were left reasoning backward from wreckage and fragments. While attending a trade show around this time, Warren saw a device called the Miniphone, a tiny reel-to-reel recorder designed for clandestine audio recording. The idea arrived immediately. a device that continuously recorded cockpit voice and flight instrument data, crash-protected, recoverable after any accident. Warren built the first prototype at the Aeronautical Research Laboratories in 1956. He circulated a report on the concept internationally. It was rejected by airlines who worried about crew privacy, by aviation authorities who questioned the cost, and by the Australian government who saw no urgency. An English Air Vice Marshal visiting Warren's laboratory in 1958 saw the prototype and brought it to British attention. The UK Ministry of Aviation supported development. Production rights went to a British firm. Australia, the country that invented the flight recorder, was the first country to make it mandatory in 1960. The United States followed in 1967. The device was mandatory on commercial aircraft worldwide within a decade of Warren's first prototype being taken seriously. Warren died in 2010 at 85. Qantas had named one of its Airbus A380s after him 2 years earlier. His father had died in a crash that would never be explained. His invention has resolved every major commercial aviation accident investigation of the modern era in which the recorders were recovered. Before any flight data recorder is certified for installation on a commercial aircraft, the crash-survivable memory unit inside it must pass 5 sequential tests, each one derived from a real crash scenario that showed what the recording unit needed to survive. These are not simulations. The test equipment is capable of destroying almost anything. The CSMU is supposed to survive it anyway. The first test is crash impact. The CSMU is loaded into an air cannon and accelerated to produce a deceleration force of 3,400 times the force of gravity, sustained for 6.5 milliseconds. To understand the scale, 3,400 game is the deceleration equivalent of going from 500 kilometers per hour to a complete stop in 45 centimeters. A person subjected to this force for 6.5 milliseconds would experience forces roughly 25 times greater than the most extreme fighter pilot maneuvers ever recorded. The CSMU is the projectile. The cannon fires it into a fixed concrete wall. After impact, the memory boards must be readable. The second test is static crush. 5,000 pounds per square inch of pressure is applied simultaneously to all 6-axis faces of the unit for 5 minutes. This replicates the compression forces applied to components buried under structural debris in a collapsed fuselage. The 5,000 psi figure is the equivalent of approximately 350 atmospheres, the pressure found at roughly 3,500 meters depth in the ocean, applied against a flat surface for 5 minutes. After the crush, the data must be readable. The third test is penetration resistance. A 230 kilogram weight with a 6 mm hardened steel pin protruding from its base is dropped from 3 meters onto the CSMU's most vulnerable access point. This replicates the force of structural debris driven into the recorder during an impact or structural collapse. The pin, with 230 kilograms behind it, impacts the cylinder at the location most likely to allow breach. The data must remain readable. The fourth test is fire. The CSMU is placed inside a propane-sourced fireball, with 3 burners positioned around it and held at 1,100 degrees Celsius for 1 full hour. After the hour-long fireball, it is moved to a sustained heat environment and held at 260 degrees Celsius for a further 10 hours. The reason for the second stage is to replicate the smoldering heat of an aircraft fire after the initial fuel fire exhausts. A crash site may burn at lower temperature for many hours after the peak fire has subsided, and the recorder must survive both phases. 1,100 degrees Celsius, for reference, is hotter than molten cast iron. The fifth test is deep water immersion. The CSMU is subjected to the hydrostatic pressure equivalent of 6,000 meters depth in salt water, sustained for 30 days. After all 5 tests, in sequence, the same unit, the memory boards are removed and read. If all recorded data is intact, the unit is certified. If a single test damages the data beyond recovery, the design fails and the unit returns to the drawing board. The CSMU passes these tests because it is built as a series of concentric defenses, each one targeted at a different failure mode. At the center is the memory board stack, stacked arrays of solid-state flash memory chips, the same fundamental technology as the solid-state drives in laptop computers, but manufactured to a far higher specification and mounted in a geometry that distributes mechanical stress. Around the memory boards is a thin aluminum housing that holds them in position and provides a sealed environment. Around the aluminum housing is the thermal protection layer, 1 inch of dry silica insulation material similar in principle to the ceramic tiles on the space shuttle, but in a different form. Dry silica is an exceptional thermal insulator. During the 1-hour, 1,100-degree fire test, the temperature at the memory board surface, inside the silica layer, must not exceed 125 degrees Celsius. 1 inch of dry silica achieves this against a fire that is hotter than molten iron for a full hour, because the thermal conductivity of the material is so low that heat cannot penetrate to the interior in the time available. This is the entire function of the middle layer, to buy time. If the fire lasts more than an hour at that temperature, the silica will eventually conduct enough heat inward to destroy the memory. The 1-hour test is calibrated to the duration of a fuel-fed aircraft fire before the fuel is exhausted. The outer layer is the structural armor, a shell of stainless steel approximately 6 millimeters thick, or titanium, where weight reduction is a priority. This layer resists the impact force, distributes the static crush, and stops the penetration pin. It is the impact defense that allows the thermal insulation inside to remain intact. A crushed or breached outer shell would allow fire or water to bypass the silica layer entirely. The 3 layers have to work together in sequence, or none of them work at all. On June 1, 2009, Air France Flight 447, an Airbus A330 carrying 228 people from Rio de Janeiro to Paris, disappeared over the mid-Atlantic at 3 o'clock in the morning in total radar darkness during a thunderstorm. No distress call, no final transmission. The aircraft simply stopped responding. Debris and 50 bodies surfaced in the days that followed, but the main wreckage and the flight recorders sank to the floor of the Atlantic at approximately 3,900 meters depth, well below the 6,000-meter design specification of the recorders, but in genuinely deep ocean. The underwater locator beacon on each recorder pinged at 37.5 kilohertz once per second. Search teams listened. For 30 days, no signal was detected in the right area. The beacons exhausted their batteries. The recorders went acoustically silent. All that was known was that the aircraft had gone down somewhere in a search area the size of a small country. 4 separate search operations over 2 years failed to find the main wreckage. A 5th operation in March 2011 started at a 37-kilometer radius around the last known position and began systematically scanning the ocean floor with sonar. On April 3, 2011, 23 months after the crash, a submarine equipped with a camera reached a debris field on the ocean floor and confirmed the wreckage of Flight 447. On May 1 and May 2, 2011, the FDR and CVR were recovered. They had spent nearly 2 years at 3,900 meters depth without any functional locator beacon. Investigators downloaded the data, every parameter, every word of audio for the final 2 hours. The crash-survivable memory units, having received no pings at all from their locator beacons for 23 months, had protected their contents through the entire period. The investigation concluded within months. Failed pitot tube sensors, a brief interruption to airspeed indications, 2 co-pilots who lost situational awareness and failed to identify and recover from an aerodynamic stall. The crash was resolved. 228 deaths explained. The engineering worked exactly as designed. On March 8, 2014, Malaysia Airlines Flight 370, a Boeing 777 carrying 239 people from Kuala Lumpur to Beijing, disappeared. It was last seen on military radar over the Gulf of Thailand. Satellite data indicated the aircraft continued flying for approximately 7 hours, executing course changes before presumably running out of fuel somewhere in the southern Indian Ocean west of Australia. Search teams deployed immediately. The search area, based on satellite handshake data, was enormous, an arc of ocean spanning thousands of kilometers of the least surveyed stretch of ocean on Earth. The underwater locator beacons on the flight recorders would be pinging. Recovery teams just needed to get close enough to hear them. In early April 2014, an Australian naval vessel towing a hydrophone array detected 4 acoustic signals in the southern Indian Ocean at a frequency consistent with a flight recorder ULB. The signals lasted for 13 minutes, 32 minutes, 5.5 minutes, and 7 minutes across 4 detections. Then they stopped. The batteries, rated for 30 days from water contact, had exhausted. Subsequent analysis of the signals raised questions about whether they were actually from the aircraft's recorders or from other acoustic sources. An interim investigation report released in March 2015 disclosed a detail that changed how the aviation world understood what had happened. The underwater locator beacon battery on the flight data recorder had expired in December 2012, 15 months before the aircraft disappeared. Maintenance records showed no evidence it had ever been replaced. The recorders are almost certainly at the bottom of the Indian Ocean, almost certainly intact. The crash-survivable memory units were built to survive 6,000 meters of water pressure for 30 days. The Indian Ocean in the search area is approximately 4,000 meters deep. If the recorders are there, the data inside them is almost certainly readable. But the ULB that was supposed to tell recovery teams where to listen was dead before the flight even departed. And the ocean floor has not given up the aircraft. Air France 447 and MH370 are the two most expensive and consequential flight recorder recoveries in aviation history. In one, the engineering did everything it was asked to do, survived 2 years at depth, yielded complete data, resolved a disaster. In the other, a $9 battery replacement that was never done made the engineering irrelevant. The recorder almost certainly survived. It just cannot be found. The device was designed to survive what the plane didn't. The problem no engineer designed against was a maintenance lapse that made it unsearchable. 2 devices in the tail, separated so one survives what destroys the other. A crash-survivable memory unit inside each. Aluminium around the memory boards, an inch of dry silica around that. Titanium or stainless steel around the silica. A unit that has been fired from an air cannon, compressed on 6 faces simultaneously, had a steel pin driven through its most vulnerable point, sat inside a 1,100-degree propane fireball for an hour, and spent 30 days at 6,000 meters of simulated ocean pressure. All before it was ever installed in an aircraft. Mounted in the tail so it decelerates last. Connected to a locator beacon that pings 37.5 kilohertz once a second from the moment water touches it. Valid for 30 days. Battery with a 6-year service life that must be replaced on schedule. The device designed to survive what the plane doesn't has done it, repeatedly, in accidents where every other piece of the aircraft was destroyed. David Warren's father died in a crash that could not be explained. The invention David Warren built in his memory has explained nearly every crash since.